Tonight, we're going to explore one of the most extraordinary questions in all of science. Why will a piece of human metal outlast every star in the Milky Way? And the answer begins with a single spacecraft, Voyager 1, the most distant and arguably the most enduring object that human beings have ever created. We build our monuments out of stone. We build them to last, to outlive us, to outlive our children, to say something permanent into the silence of time. The pyramids of Gliese have stood for 4,500 years, the Roman Colosseum for nearly 2,000, Stonehenge for 5. We look at these things and we call them eternal. We call them the greatest achievements of our civilization. We take photographs of them. We write about them. We build museums around them and charge admission to stand near them and feel for a moment the weight of all that accumulated time. And every single one of them is going to crumble, not because they were built poorly, not because the people who built them lacked ambition or skill, but because they were built on Earth. And Earth, as it turns out, is one of the most destructive environments in the known universe for anything that human beings have ever tried to make permanent. Rain, wind, salt air, acid in the atmosphere, the slow biological work of lichen and moss and root systems, the grinding patience of freeze and thaw cycles, working at stone over centuries, even sealed underground, even preserved in the driest desert on the planet. Everything we have ever built is fighting a losing battle against the planet it was built on. But here is the thing none of those monuments can claim. None of them are leaving. In September of 1977, engineers at NASA launched a spacecraft that weighed roughly the same as a small car. It was built from aluminium and copper and gold-plated records and 1970s electronics that would look primitive by today's standards. It had no pilot. It had no way to come home. It had no mission to land anywhere or to be retrieved or to return any physical samples to Earth. It was aimed deliberately and precisely at the permanent dark beyond everything we have ever known. That spacecraft is Voyager 1. And right now, tonight, as you settle in and close your eyes, it is still moving, still transmitting, still sending its signal home across a distance so large that the signal itself, traveling at the speed of light, takes nearly a full day to reach us. It crossed beyond the edge of our solar system in 2012, piercing the heliopause, the boundary where the sun's magnetic influence finally gives way to the true interstellar medium, the space between the stars. As of 2021, it had already traveled more than 152 astronomical units from Earth. That is 152 times the distance from here to the sun. In kilometers, that is a number with 13 digits. It is the most distant human-made object in existence by a very large margin. Nothing else humanity has ever built is even close. And it is not slowing down. Here is the question that tonight is built around. Here is what we are going to sit with together for the next few hours, slowly, gently, without any urgency at all. The pyramids will erode. The Colosseum will crumble. Given enough time, millions of years, hundreds of millions, the land they stand on will be reshaped by tectonics, flooded by rising oceans, buried under the advance of glaciers. The Earth itself will eventually be consumed by the sun when it expands into a red giant, roughly 5 billion years from now. The oceans will boil. The atmosphere will be stripped away. Every mountain range we have ever named, every river we have ever mapped, every city we have ever built, all of it will be gone. And when that happens, when every pyramid has long since turned to dust, when every cathedral has been dissolved by acid rain over geological time, when the last trace of human biology has dissolved back into the chemistry of a dead and airless rock, Voyager 1 will still be out there, drifting through the dark between the stars, silent because its power will have run out decades earlier, but utterly undamaged, utterly intact, carrying a golden record engraved with the sounds of Earth, whale song, wind, rain, music, laughter, the voices of children, through a void so cold and so empty and so perfectly still that the very concept of decay has no meaning inside it. Because out there, in the interstellar vacuum, there is no oxygen to rust the metal, no water to corrode it, no weather to erode it, no atmospheric friction to drag at it, no bacteria to break it down, no acid rain, no freeze-thaw cycles, no gravity strong enough at these distances to pull it into anything. The forces that have been destroying everything we have ever built on Earth, every single one of them, simply cease to exist in the deep void between the stars. And so, a 1-ton machine assembled by human hands in a laboratory in Pasadena, California, nearly 50 years ago, has achieved something that no pyramid, no cathedral, no monument we have ever raised has come remotely close to achieving. It has escaped the thing that destroys everything. It has become very nearly immortal. Tonight, we are going to follow it. Slowly, at a pace that matches the dark and the quiet of wherever you are right now. We will trace the story of how Voyager 1 was built and why it was sent and what it found on the way out. We will follow it past the edge of the solar system and into the interstellar medium. We will track the extraordinary, living, present tense engineering work being done right now, tonight, in May 2026, to keep it alive for as long as possible. And then we will let it go. We will follow its trajectory forward, through the Oort Cloud, past the nearest stars, through the death of the sun, through the slow extinction of the last stars in the galaxy, into a universe so old and so dark that our human language barely has words for the timescales involved. And at the end of all of it, Voyager 1 will still be moving. There is nothing you need to do, nowhere you need to be, no argument you need to follow, no test at the end, no need to remember any particular number or name. Just settle in, close your eyes if you like, and let the story carry you. Voyager 1 has been drifting for 47 years. It knows how to do this. To understand where Voyager 1 is going and why it will outlast everything, we need to go back to the beginning. Not the beginning of the universe, the beginning of a question that a small group of engineers and mathematicians in California asked themselves in the middle of the 1960s. The question was simple, almost embarrassingly simple. When would the planets line up? A young mathematician named Gary Flandreau was working at JPL, the Jet Propulsion Laboratory in Pasadena, California, in 1965, when he was given a fairly routine assignment. He was asked to look at upcoming mission opportunities and identify any interesting windows for spacecraft trajectories to the outer solar system. The outer planets, Jupiter, Saturn, Uranus, and Neptune, had never been visited by a spacecraft. They were known quantities from telescopic observation, but up close, they were complete unknowns. Nobody had ever sent anything out that far. The distances were simply too enormous, and the travel times too long for any mission that had been proposed to be practical. But Flandreau, running his calculations, noticed something. The outer planets of our solar system were about to do something they had not done in 175 years, and would not do again for another 175 years after that. They were going to align, not in a perfect straight line. That is a different and far simpler astronomical event. What Flandreau noticed was subtler and far more consequential. Between approximately 1977 and 1989, Jupiter, Saturn, Uranus, and Neptune would be arranged in such a configuration that a spacecraft launched from Earth could visit all four of them in a single continuous journey, using the gravity of each planet to slingshot itself toward the next, gaining speed with each encounter without burning any additional fuel. This is what engineers call a gravity assist, and it is worth taking a moment to understand what it actually means, because it is the mechanism that made Voyager 1's journey not just possible, but inevitable. When a spacecraft passes close to a massive planet, the planet's gravity reaches out and grabs it. As the spacecraft swings around the planet, on a carefully calculated trajectory, it does not just fall toward the planet and then fly away at the same speed. It actually gains energy. It borrows a tiny, imperceptible fraction of the planet's own momentum as it orbits the Sun. Momentum so vast and the spacecraft so small that the planet will never notice the transaction. But to the spacecraft, that borrowed momentum is transformative. Each gravity assist can add thousands of kilometers per hour to the spacecraft's velocity. Think of it this way. Imagine you are standing on a railway platform and a very fast train goes past you without stopping. If you could somehow grab hold of the train, swing around it, and then let go, you would be moving much faster than before you grabbed it, in the direction the train was going. That is the principle of a gravity assist. You are borrowing momentum from something enormous and giving it back invisibly, while keeping the energy it transferred to you. With the 1977 alignment, NASA had the opportunity to do this not once, but 4 times in sequence, using the 4 largest planets in the solar system as a chain of slingshots. The mathematics were extraordinary. A spacecraft launched on the right trajectory in 1977 could reach Jupiter in 18 months, use Jupiter's gravity to fly onto Saturn, use Saturn's gravity to fly onto Uranus, and use Uranus's gravity to fly onto Neptune. A complete tour of the outer solar system in a single mission, in a time frame that would otherwise have been physically impossible. Flandreau called it the Grand Tour. The window for this alignment would open in 1977 and close by the early 1980s. After that, the planets would drift apart in their orbits, and the geometric opportunity would not recur until the 2150s. Anyone alive to plan the mission would be dead before it came around again. So NASA moved quickly. The program that emerged was called Voyager. From the beginning, the decision was made to build 2 spacecraft rather than 1. Deep space is unforgiving, and the engineers at JPL understood that a single point of failure in a mission of this scope, a mission that could not be rescued, repaired, or retrieved once it had launched, was a risk too large to accept. 2 spacecraft would be built identically, launched on different trajectories, so that if one failed, the other might still succeed. Voyager 2 launched first on August 20th, 1977, on a slower, more fuel-efficient trajectory that would allow it to reach all 4 outer planets, the full Grand Tour. Voyager 1 followed 16 days later, on September 5th, 1977, on a faster trajectory designed to reach Jupiter and Saturn more quickly. But Voyager 1's trajectory came with a trade-off. The faster path to Saturn required a specific close encounter with Saturn's largest moon, Titan, and that Titan flyby, as we will see, would fling Voyager 1 sharply out of the plane of the solar system, ending any possibility of continuing on to Uranus and Neptune. Voyager 1 would not complete the Grand Tour, but it would go farther and faster than any other spacecraft in history. Both spacecraft were carried into space by a Titan III-E Centaur rocket, a two-stage rocket roughly 48 meters tall, burning a combination of liquid hydrogen, liquid oxygen, and solid fuel boosters. The launch from Cape Canaveral in Florida was, by the standards of the era, routine. The spacecraft separated from the upper stage of the rocket, its onboard systems activated, and it began its journey outward. The spacecraft itself is worth describing in some detail, because understanding what Voyager 1 is, physically, materially, is essential to understanding why it will last so long. It weighs approximately 722 kilograms fully fueled. That is roughly the mass of a small car, or a concert grand piano, or, if you need a more vivid comparison, approximately the combined weight of 9 average adult humans. It is not a large object by any measure that matters here on Earth. It would fit easily in a single-car garage. Its most visually dominant feature is the high-gain antenna, a parabolic dish 3.7 meters in diameter, roughly the size of a large backyard trampoline. This antenna is the spacecraft's voice. It is how Voyager 1 talks to Earth. Every piece of scientific data it has ever sent back, every image of Jupiter's storms, every measurement of Saturn's magnetic field, every reading of the interstellar plasma it is moving through right now, has been transmitted through this dish across billions of kilometers of empty space to the enormous radio receivers of NASA's deep space network here on Earth. Extending from the main body of the spacecraft is a long boom carrying the magnetometer instruments, the sensors designed to measure the magnetic fields of the environments through which the spacecraft passes. On the other side, a second boom carries the 3 RTGs, the radioisotope thermoelectric generators, that provide all of the spacecraft's electrical power. An RTG deserves a careful explanation because it is one of the most elegant engineering solutions in the history of spaceflight, and because it is directly responsible for why Voyager 1 is still alive today. Out in the outer solar system and beyond, solar panels are essentially useless. Sunlight weakens with the square of distance. Double the distance from the sun and you get 1/4 of the light. By the time you reach Jupiter, sunlight is already 27 times weaker than it is on Earth. By Saturn, it is 90 times weaker. By the heliopause, where Voyager 1 now drifts, it is thousands of times weaker. A solar panel the size of a football pitch would generate almost nothing at these distances. So the Voyager spacecraft do not use solar panels. They use the heat generated by the radioactive decay of plutonium-238, a specific isotope of plutonium chosen for its long half-life and the steady, predictable nature of its decay. As the plutonium atoms break down, they release heat. That heat is converted into electricity through a process called the thermoelectric effect, the same principle that causes an electrical current when 2 different metals are joined and heated unevenly. The conversion is not efficient by modern standards, but it requires no moving parts, no maintenance, no fuel supply, and no external power source. The plutonium decays, the heat flows, the electricity is generated, automatically, continuously, without any human intervention required. Voyager 1 launched with 3 RTGs, producing a combined electrical output of approximately 470 watts, roughly what it takes to run a medium-sized room heater. That was enough to power all 10 of its scientific instruments, plus all of its onboard computers, its transmitter, its attitude control systems, and the heaters that kept critical components from freezing in the cold of deep space. By 2026, after nearly 5 decades of decay, the RTGs are producing somewhere around 230 watts. just under half of what they started with. And this declining power is the central tension of Voyager 1's present-day story. The slow, graceful, mathematically inevitable countdown that has been running since the day the spacecraft launched. But in 1977, with 470 watts of clean nuclear power humming in its RTGs and the alignment of the outer planets waiting ahead, Voyager 1 began the journey that nobody who planned it would live long enough to see completed. The first stop was Jupiter. The spacecraft arrived in March 1979, having covered roughly 650 million kilometers in 18 months. To put that in perspective, 650 million kilometers is more than 4 times the average distance from the Earth to the Sun. Voyager 1 covered it in a year and a half. It was, at that point, moving faster than any human-made object had ever moved before. What it found at Jupiter redrew our understanding of the solar system almost immediately. Jupiter is the largest planet in our solar system, more than twice the mass of all the other planets combined. A world so large that 1,300 Earths could fit inside it. It had been studied through telescopes for centuries, and much was already known about its basic properties. But knowing something through a telescope and seeing it up close are very different things, and Voyager 1's cameras and instruments revealed a Jupiter that was more dynamic, more violent, and more alive than anyone had properly imagined. The Great Red Spot, a storm that had been observed by Earth-based astronomers since at least the 17th century, was revealed as a vast rotating anticyclone, wider than the Earth itself, with internal wind speeds exceeding 500 kilometers per hour. The clouds of Jupiter's atmosphere were shown to be arranged in complex bands and zones of different chemical compositions, swirling and interacting in patterns that took years of analysis to begin to understand. The spacecraft discovered 3 new moons of Jupiter that had not been known to exist before the flyby: Thebe, Metis, and Adrastea. It discovered that Jupiter had a faint ring system, not the spectacular rings of Saturn, but a thin, dark structure of dust and debris orbiting close to the planet. This was the first time rings had been confirmed around any planet other than Saturn, and it changed the way planetary scientists thought about the structure of the solar system's giant planets. But it was one of Jupiter's existing moons, Io, the innermost of the 4 large moons that Galileo had first observed in 1610, that produced the single most astonishing discovery of the primary mission. Before Voyager 1's flyby, the scientific consensus about Io was that it would look broadly similar to our own moon: old, cratered, geologically quiet, a passive remnant of an earlier, more violent time in the solar system's history, its surface unchanged for billions of years. What Voyager 1 showed was something nobody in the planetary science community had been prepared for. Io was not geologically quiet. It was the most volcanically active body in the entire solar system. Its surface was not covered in ancient impact craters, because the constant flow of volcanic material had buried and erased all of them. Instead, there were volcanic calderas, lava plains, enormous sulfur deposits painting the surface in shades of yellow, orange, red, and white that made Io look, in the words of one of the mission scientists, like a pizza. And most dramatically of all, Voyager 1's cameras caught active volcanic eruptions in progress, plumes of material being ejected hundreds of kilometers above the surface while the spacecraft watched. It was one of the great moments of confirmation in the history of science, and it came with a timing so precise it bordered on the theatrical. Just 3 days before Voyager 1's closest approach to Io, on March 2nd, 1979, a scientific paper was published in the journal Science by 3 researchers: Stanton Peele of the University of California, Santa Barbara, Patrick Casson of NASA's Ames Research Center, and Ray Reynolds, also of Ames. Their paper was titled Melting of Io by Tidal Dissipation. In it, they calculated that the gravitational tug-of-war between Jupiter and Io's neighboring moons, Europa and Ganymede, should be generating enormous amounts of heat inside Io through a process called tidal flexing. Jupiter's gravity pulls one way, the other moons pull another way, and Io is squeezed and stretched rhythmically in the middle, like a rubber ball being kneaded in a fist. That mechanical energy, Peele, Casson, and Reynolds calculated, had to go somewhere, and the most likely place was upward as volcanic heat. Their conclusion, in the paper: we predict widespread and recurrent surface volcanism. 3 days later, Voyager 1 confirmed it. 3 days between the prediction and its proof. In a field where it sometimes takes decades to confirm a hypothesis, that is a kind of scientific lightning. From Jupiter, Voyager 1's gravity-assisted trajectory carried it onward to Saturn. It arrived in November 1980. Saturn, seen by Voyager 1 at close range, was its own kind of revelation. The rings of Saturn had been known since Galileo first observed them in 1610. He thought, looking through his primitive telescope, that Saturn had ears. Christian Huygens, working with a better instrument in 1655, correctly identified them as a flat disk surrounding the planet. But from Earth, even through the best telescopes, the rings appeared as a single, smooth, broad structure divided into a handful of distinct bands. What Voyager 1 showed was something almost incomprehensibly more complex. The rings were not a handful of bands. They were thousands of individual ringlets, structure of extraordinary intricacy that stretched across hundreds of thousands of kilometers, but was, in places, less than a kilometer thick. Within those ringlets were structures that defied the physics the scientists had expected to find. There were braided ringlets, 2 strands woven around each other in a pattern that should have unwound and separated over time, but hadn't. There were sharp, clean edges where gradual transitions should have been. And most puzzling of all, there were what the Voyager scientists called spokes, dark, radial markings that appeared on the rings and rotated with them, like the spokes of a wheel, rather than orbiting independently the way particles at different distances from the planet should. Spokes should not exist. The orbital mechanics of the rings dictated that particles at different distances from Saturn should orbit at different speeds. Faster closer in, slower further out. And any radial structure should therefore shear apart almost immediately, like a line drawn in flowing water. The spokes persisted. They were real. And to this day, decades after Voyager 1 photographed them, their precise mechanism is still not fully understood. But it was Saturn's largest moon, Titan, that dictated the entire subsequent history of Voyager 1's journey. Titan had been discovered by Christian Huygens in 1655, the same astronomer who identified Saturn's rings. It was known to be large, slightly larger than the planet Mercury. And in 1944, the astronomer Gerard Kuiper had detected an atmosphere. An atmosphere around a moon was extraordinary in itself. No other moon in the solar system was known to have one. Titan's atmosphere turned out to be dense, denser, in fact, than Earth's, and composed primarily of nitrogen, with complex organic molecules forming in the upper layers and producing a thick, opaque orange haze that prevented Voyager 1's cameras from seeing the surface. What Voyager 1 found at Titan was both revealing and tantalizing. The atmosphere was confirmed to be nitrogen-dominated with significant methane, and the organic chemistry happening in the upper atmosphere was of extraordinary scientific interest. The kind of complex carbon chemistry that, on the early Earth, may have been a precursor to the molecules of life. But the surface remained hidden, shrouded beneath that impenetrable orange haze. The question of what lay beneath it would not be answered until the Cassini-Huygens mission, decades later. To get close enough to Titan to conduct the detailed atmospheric measurements the scientists wanted, Voyager 1 had to fly over Saturn's North Pole on a very specific trajectory, one that brought it in close to Titan, but then flung it sharply upward, 35 degrees out of the flat plane of the solar system. The ecliptic plane, as it is called, is the broad, flat disk in which all the planets orbit. Voyager 2 would continue in that plane and go on to Uranus and Neptune. Voyager 1 would not. It would be deflected upward and outward on a heading that would carry it out of the solar system entirely, never to encounter another planet. This was not an accident. It was a deliberate choice by the mission planners, who understood that what Titan could tell them about organic chemistry and atmospheric science was worth more than the opportunity to continue the grand tour. Voyager 2 would handle Uranus and Neptune. Voyager 1 was going somewhere else, somewhere no spacecraft had ever gone. Its primary scientific mission was effectively over. Everything it had been designed and built and launched to do, Jupiter, Io, Saturn, Titan, was complete. The images had been taken. The data had been collected. The papers would be written and the textbooks revised and the discoveries celebrated for decades. And the spacecraft kept going because it had no other option, because there was nothing in its path to stop it, because the engineers who built it had given it enough plutonium to keep its systems running for decades and enough engineering margin to keep transmitting for as long as the power held out. And because the solar system, vast as it is, turned out to be only the beginning of the journey, Voyager 1 was heading for the edge of everything we had ever known, and it would take 35 more years to get there. After Saturn, the mission changed. Not officially, not yet. NASA's formal primary mission continued running for several more years, and the engineers and scientists at JPL were still monitoring everything carefully, still reading the data, still running the numbers. But the nature of the journey had transformed in a way that everyone involved understood, even if the paperwork hadn't caught up yet. Jupiter was behind them, Saturn was behind them, Titan was behind them. The 12 photographs of Io's volcanoes, the braided ringlets of Saturn, the opaque orange haze of Titan's atmosphere. All of it was captured, stored, transmitted back to Earth, and entered into the scientific record. The spacecraft had done everything it was designed to do, and it kept going, because there was nothing to stop it. Because the void ahead was frictionless and vast and completely indifferent to whether Voyager 1 had completed its primary mission or not. The physics of the situation was simple and absolute. The spacecraft was moving. There was nothing in its path to slow it down, and so it moved. For the next 2 decades after Saturn, Voyager 1 drifted outward through the vast invisible structure that surrounds our entire solar system. A structure that most people have never heard of, and that had never been directly explored by any spacecraft before: the heliosphere. The heliosphere is not easy to picture because it is invisible, intangible, and enormous, but understanding it is essential to understanding everything that comes next in Voyager 1's story. So let us take a moment to build the picture carefully. The Sun is not a passive object. It is constantly active, constantly exhaling, releasing a continuous stream of charged particles, primarily electrons and protons, that flows outward in all directions at speeds ranging from roughly 300 to 800 kilometers per second. This is called the solar wind. It has been blowing continuously for the entire 4.6 billion year history of the solar system. And it does not just blow out into the galaxy and disappear. It pushes. Specifically, it pushes against the thin, cold gas and dust of the surrounding interstellar medium, the material that fills the space between the stars. The solar wind exerts an outward pressure, and the interstellar medium exerts an inward pressure. And the place where those two pressures balance, where the solar wind can no longer push any further out and the interstellar medium can no longer press any further in, is a boundary. A vast egg-shaped boundary surrounding the entire solar system, all 8 planets, the Kuiper Belt, and everything else we have ever explored. That boundary is called the heliopause. Inside the heliopause is the heliosphere, the Sun's magnetic territory, its sphere of influence, the region of space that is, in a very real sense, ours. Outside the heliopause is interstellar space, the space between the stars, the true void. When Voyager 1 left Saturn in November 1980, it was at roughly 10 astronomical units from the Sun. The heliopause was somewhere out ahead, but nobody knew exactly where. Before Voyager 1, the size of the heliosphere was genuinely unknown. Some estimates had put it as close as the orbit of Jupiter, 5 times the Earth-Sun distance. Others put it much farther out. The only way to know for certain was to send something there. Voyager 1 was going there. But first, it would pass through 2 intermediate boundaries that nobody had ever visited before. The first of these is called the termination shock. Inside the heliosphere, the solar wind flows outward supersonically, faster than the speed of sound in the surrounding medium. But as it travels farther and farther from the Sun, it loses energy. It spreads out across an ever larger volume of space, and at a certain distance, something happens. The solar wind abruptly slows down from supersonic to subsonic speeds, like an aircraft dropping below the speed of sound, producing a kind of cosmic sonic boom, a standing shockwave that marks the point where the outward rush of the solar wind is first significantly impeded by the pressure of the interstellar medium. This is the termination shock. It is the first indication that the solar wind is losing its battle against the universe outside. On December 15, 2004, after 27 years of travel, Voyager 1 crossed the termination shock at a distance of 94 astronomical units from the Sun. The data came back in real time. Instruments recording the sudden change in particle energies, the shift in the behavior of the solar wind, the first direct measurements of a region of space that had existed in theoretical models for decades but had never been touched. The spacecraft had entered the heliosheath, the outermost layer of the heliosphere, a turbulent region filled with slowed and heated solar particles. The solar wind here was not blowing outward freely anymore. It was compressed, heated, chaotic, pushed back against itself by the pressure of the interstellar medium on the other side of the heliopause. Voyager 1 was inside a kind of cosmic compression zone, drifting through a region of space where the Sun's influence was fighting its last battle against the void. It would take another 8 years to cross it. Those 8 years, from the termination shock crossing in December 2004 to the heliopause crossing in August 2012, were years of intense scientific watching. The instruments aboard Voyager 1 were measuring everything they could, sending data back at 160 bits per second across a distance that was growing by 3.5 astronomical units every year. The scientists at JPL and the University of Iowa and institutions around the world were parsing that data carefully, watching for the telltale signs that the heliopause was approaching. The problem was that the one instrument best suited to detecting the heliopause, the plasma instrument, which directly measures the density and temperature of charged particles, had stopped working years earlier, during the Saturn encounter in 1980. A component had failed, and from that point on, Voyager 1 had to piece together its picture of the surrounding environment using the other instruments it had available: the magnetometer, the cosmic ray detectors, the low-energy charged particles instrument, the plasma wave subsystem. It was like trying to see in the dark using only your sense of touch. But the scientists were patient, and the data kept coming. By 2010 and 2011, something was clearly changing. The count of low-energy particles originating from the sun, the outer fringes of the solar wind, was dropping. The count of high-energy cosmic rays coming in from outside the solar system was rising. The magnetic field readings were behaving differently. Something was ahead. And then, on August 25th, 2012, it happened. The data that reached Earth from Voyager 1 that month showed something definitive. High-energy particles from the sun vanished, a sign that the rest of the solar wind had been left behind. Cosmic rays from beyond the solar system, which the heliosphere partially blocks, intensified after the passage. The changes were sharp, clear, and unprecedented. The spacecraft was somewhere new, but the team needed proof, not just circumstantial evidence from particle counts, but direct measurement of the plasma density, the specific fingerprint of interstellar space that the broken plasma instrument could no longer provide directly. That proof came the following spring. On April 9th, 2013, the plasma wave subsystem on Voyager 1, the instrument that listens for the vibrations of charged particles like a microphone pressed against the hull of the spacecraft, detected something it had never detected before in interstellar space: locally generated electron plasma oscillations at a frequency of approximately 2.6 kilohertz. The frequency of those oscillations is directly related to the density of the surrounding electron plasma. It is a measurement as precise and specific as a fingerprint. That oscillation frequency corresponded to an electron density of about 0.08 electrons per cubic centimeter, very close to the value expected in the interstellar medium. Inside the heliosphere, the electron density had been around 0.002 electrons per cubic centimeter. Outside, in interstellar space, the expected value was somewhere between 0.05 and 0.22. Voyager 1's reading of 0.08 fell squarely within that range. The plasma wave science team went back through its data and found an earlier, fainter set of oscillations from October to November 2012. Through extrapolation from both sets of measurements, they determined that Voyager 1 had first entered interstellar space in August 2012, consistent with all the other instrument readings that had been puzzling the team for months. Don Gurnett, the University of Iowa physicist who led the plasma wave science team and who had been working on the Voyager mission since the 1970s, described the moment when his team realized what they were looking at. He said they literally jumped out of their seats when they saw these oscillations in the data. They showed that the spacecraft was in an entirely new region, comparable to what was expected in interstellar space, and totally different from anything inside the solar bubble. Ed Stone, still the Voyager project scientist after 4 decades, called it humankind's historic leap into interstellar space. NASA waited 13 months after the probable crossing date before making the official announcement. Not from secrecy and not from excessive caution for its own sake, but because the heliopause crossing had been actively controversial within the scientific community for months, and the team wanted to be certain. The holy grail of heliospheric research had been to reach the heliopause, and the team was not going to announce it without evidence that was beyond dispute. The plasma oscillation data, when it finally arrived and was analyzed and confirmed, was that evidence. On September 12, 2013, the paper by Gurnett and his colleagues was published in the journal Science, and the announcement was made after 36 years of travel, after leaving Earth on a Titan 30 Centaur rocket in the summer of 1977, after swinging past Jupiter and Saturn and Titan and then drifting outward through the heliosheath for 8 years. Voyager 1 had become the first human-made object to enter the space between the stars. Now let us talk about where it is tonight. As of May 2026, Voyager 1 is approximately 172 astronomical units from Earth. Let us make that number real for a moment, because astronomical units are a unit of measurement that our brains are not naturally equipped to process. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 150 million kilometers. It takes light, traveling at 300,000 kilometers per second, about 8 minutes and 20 seconds to cover that distance. That is the standard unit of measurement for distances within our solar system. Voyager 1 is 172 of those distances away from Earth right now. In kilometers, that is approximately 25.7 billion kilometers. 25.7 billion. If you wanted to drive that distance at motorway speeds, 100 kilometers per hour, no stops, 24 hours a day, it would take you approximately 29 million years. A signal from Voyager 1, traveling at the speed of light, takes approximately 23 hours and 56 minutes to reach Earth. Just under 1 full day one way. When the engineers at JPL send a command to the spacecraft, turn this instrument on, adjust that thruster, check this system, they will not know if the command was received for almost a full day. And then they must wait another full day for the response. A round-trip communication takes nearly 48 hours. A question asked on Monday is answered by Wednesday. And Voyager 1 is approaching a milestone that no human-made object has ever reached before. On November 15, 2026, Voyager 1 will cross a distance of 1 full light day from Earth. A light day is exactly what it sounds like. The distance that light covers in 24 hours, traveling at 300,000 kilometers per second for an entire day without stopping. That is approximately 25.9 billion kilometers. No spacecraft, no probe, no piece of human engineering has ever been this far from the planet it was built on. Voyager 1 will cross that line before the end of this year. Susie Dodd, who has served as Voyager project manager at JPL, has described what that milestone feels like from the inside. She said that if she sends a command and says good morning at 8 o'clock on a Monday, she will receive Voyager's acknowledgement back at approximately 8 o'clock on Wednesday morning. That is the current reality of the mission, a greeting that takes 2 full days to be returned. But here is what makes the present moment in Voyager 1's story so alive, so charged, so urgent. Despite the vast distances and the apparent simplicity of a spacecraft just moving in a straight line through empty space, the spacecraft is dying. Slowly, gracefully, entirely on schedule, but dying. The RTGs that have powered Voyager 1 since 1977 are following the implacable mathematics of radioactive decay. The plutonium-238 that was loaded into those generators nearly 5 decades ago has a half-life of 87.7 years. That means that every 87.7 years, half of the remaining plutonium decays away, and the heat, and therefore the electricity, is halved. The RTGs lose approximately 4 watts of power every year. That does not sound like much. But Voyager 1 began its journey with 470 watts, and by 2026, it has roughly 230 watts remaining. And every single watt matters because the spacecraft must allocate those watts across its transmitter, its onboard computers, its attitude control systems, its heaters, and whatever science instruments are still running. When the power drops below the threshold needed to keep a system running, that system must be shut down. There is no way around it. No alternative power source. No way to recharge. Just the slow, inevitable decline of the atoms themselves, losing their radioactivity by degrees, giving out less heat each year than the year before. This has forced the Voyager team into a long and painful series of decisions across the decades. Each instrument shutdown is permanent. Each one represents data that will never be collected, questions that will never be answered, measurements of the interstellar medium that only Voyager 1 is positioned to make. The cameras were turned off in 1990 after taking the pale blue dot. The plasma instrument died at Saturn in 1980. The ultraviolet spectrometer, the planetary radio astronomy instrument, the photopolarimeter system, the cosmic ray subsystem switched off in February 2025, and most recently, in April 2026, less than 3 weeks before tonight, the Low Energy Charge Particles experiment, the LECP, which had been running almost continuously since the spacecraft launched in 1977, was permanently deactivated to save power. One by one, the sensors of this spacecraft have been going dark. As of tonight, in May 2026, only 2 science instruments remain operational on Voyager 1. The plasma wave subsystem, which listens to the vibrations of charged particles in the surrounding medium, and the magnetometer, which measures the magnetic fields of the space through which the spacecraft is moving. 2 instruments out of the 10 that launched with the spacecraft. 2 windows on the universe still open, still sending their data home at 160 bits per second across 25 billion kilometers of empty space. 160 bits per second. To put that in context, the internet connection you would have had on a dial-up modem in the mid-1990s ran at around 14,400 bits per second. Voyager 1 is communicating with Earth at roughly 1/100th of that speed. And yet the data it sends back, those 160 bits per second, arriving at the enormous dishes of the Deep Space Network after a 24-hour journey at the speed of light, is irreplaceable, because it is the only data being collected in this region of space by the only human-made object that has ever been here. The transmitter that generates that signal runs on roughly 22 watts of power, about the same as a dim decorative lamp. By the time that signal reaches Earth, having spread out across 25 billion kilometers of space in all directions simultaneously, it has weakened to something in the region of 10 billion times less powerful than a digital watch battery. The engineers at JPL describe receiving Voyager 1's signal as analogous to detecting the heat from a single candle at a distance of several hundred kilometers, in a world where every other heat source has been removed. The enormous dishes of the Deep Space Network, the 70-meter antenna at Goldstone in California's Mojave Desert, and its counterparts in Madrid and Canberra, must combine their full sensitivity and point directly at Voyager 1's known position for hours at a time to pull that signal out of the background noise of the universe. The RTGs are projected to generate enough power to maintain engineering systems, the basic housekeeping functions that keep the spacecraft oriented and transmitting, until approximately 2036. After that, the power will fall below the threshold needed to keep even the most fundamental systems running. The heaters that prevent the fuel lines from freezing solid in the -270-degree cold of interstellar space, the transmitter itself, the attitude control thrusters that keep the antenna pointed at Earth. The voice will go quiet, not with a crash or a catastrophe, not because the spacecraft has broken or collided with anything, just because the atoms that have kept it alive for nearly 6 decades will have finally given too little of their warmth to sustain the electronics that depend on it. After 2036, Voyager 1 will continue its journey in complete silence. No signal, no data, no way for the people of Earth to know where it is or what it is passing through. It will drift at the same velocity, on the same heading, through the dark between the stars, alone, intact, carrying its golden record and its fading memories of Jupiter and Saturn and the pale blue dot it left behind. And that is when the real story begins, because the silence is not the end. When Voyager 1 goes quiet in the mid-2030s, it will be somewhere around 200 astronomical units from Earth. It will still be moving at approximately 17 kilometers per second. It will have been traveling for nearly 60 years, and the journey ahead of it will make those 60 years look like the first few steps of a walk that crosses a continent. In about 300 years from now, it will reach the inner boundary of the Oort Cloud, and after that, it will take approximately 30,000 more years to pass through to the other side, 300 years to reach it, 30,000 years to cross it. And after the Oort Cloud, after the very last gravitational reach of the Sun finally releases its hold entirely, Voyager 1 will enter the true open space between the stars, not just the interstellar medium in the neighborhood of our solar system, but the deep galaxy, the dark between worlds, the place where our language and our numbers begin to strain against the scale of what they are being asked to describe. That is where we are going next. After 2036, there will be silence, not the silence of failure or catastrophe, or any kind of ending that deserves those words. Just the silence of a machine that has done everything asked of it, and more, and whose power source has finally declined below the threshold required to maintain the electronics that give it a voice. The transmitter will stop. The computers that manage the antenna orientation will lose power. The gyroscopes that have kept the antenna pointed at Earth for nearly 6 decades will have nothing left to spin on. The spacecraft will still be intact. It will still be moving. It will simply no longer be able to speak, and it will not matter, because what happens next does not require a transmitter or a computer or any of the 1970s electronics that have been so carefully nursed through 5 decades of deepening cold and declining power. What happens next requires only one thing: Newton's first law of motion. An object in motion will remain in motion unless acted upon by an external force. In the interstellar medium, in the space between the stars, there are no meaningful external forces, no friction, no atmospheric drag, no gravity strong enough at these distances to meaningfully redirect a 1-ton spacecraft moving at 17 kilometers per second. The interstellar medium is not a perfect vacuum. It contains, as Stella Koch, Okker's research confirmed, a faint persistent hum of plasma, a thin background of ionized hydrogen, dust grains, magnetic fields. But these are not forces capable of slowing Voyager 1 on any timescale that matters to us, on the timescales we are about to discuss. they are essentially nothing. So Voyager 1 will simply continue, doing what it has always done, going. It will cover roughly 523 million kilometers per year, 1 light year every 18,000 years. That is a slow pace by the standards of light, which covers a light year in a single year by definition. But it is the pace of something that will never stop. And given enough time, even the slowest persistent motion produces extraordinary results. Let us trace what that motion produces. Let us follow Voyager 1 forward through time, forward past any timescale that human history has ever directly confronted, forward through the deep future of the solar system, forward into the multi-trillion-year twilight of the universe itself. The first landmark is approximately 300 years from now. In roughly 3 centuries, Voyager 1 will reach the inner boundary of the Oort Cloud. Most people, even people with a solid understanding of the solar system, underestimate the scale of what the Oort Cloud actually is. We tend to think of the solar system as the planets, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and then Pluto out on the edge. Perhaps we add the Kuiper belt, the disk of icy objects beyond Neptune in which Pluto sits. And then we imagine that interstellar space begins shortly after that. It does not. The solar system is vastly, incomprehensibly larger than its planets. The outermost planet, Neptune, orbits at roughly 30 astronomical units from the Sun. Pluto ranges between about 30 and 50 AU. The Kuiper belt extends to perhaps 50 or 60 AU. And then, well beyond the Kuiper belt, well beyond anything that has ever been visited by a spacecraft, the Oort Cloud begins. The Oort Cloud occupies space at a distance between approximately 5,000 and 100,000 astronomical units from the Sun. And NASA's Voyager 1, at its current speed, won't enter the Oort Cloud for about 300 years and won't exit the outer edge for perhaps 30,000 years. Sit with those numbers for a moment. The outermost planet is at 30 AU. The Oort Cloud begins at 5,000 AU, more than 160 times further out than Neptune. And it extends to 100,000 AU, more than 3,000 times further than Neptune, nearly 2 light years from the Sun. The Oort Cloud is not a ring or a disk like the Kuiper belt. It is a sphere, a vast, roughly spherical shell surrounding the entire solar system in every direction, like a soap bubble of ice and rock. Hundreds of billions of icy objects drifting in the cold dark at distances so enormous that the Sun, from the outer Oort Cloud, appears as just another bright star among the tens of thousands visible with the naked eye. The Oort Cloud was proposed in 1950 by the Dutch astronomer Jan Oort. He was studying the orbits of long-period comets that take hundreds of thousands or even millions of years to complete a single orbit of the Sun. And he noticed something curious. These comets did not arrive from a disk or a belt, as short-period comets do. They arrived from all directions equally. From above, from below, from the sides, from every point of the celestial sphere with apparently equal frequency. That could only mean one thing. Their source was not a flat ring, but a sphere. Oort also discovered that the aphelia, the farthest points of these comets' orbits, clustered around 20,000 AU from the Sun, suggesting a reservoir at that distance with a spherical isotropic distribution. He was right. The Oort Cloud is now the accepted scientific model for the source of long-period comets, and its existence is one of the best supported inferences in planetary science, even though no telescope has ever directly imaged a single Oort Cloud object. We know it is there because the comets it sends in our direction tell us so. Like hearing footsteps in a dark room before you see who is there. No spacecraft has ever entered the Oort Cloud. Voyager 1 will be the first. In 300 years, it will cross the inner threshold, and then it will spend the next 30,000 years drifting through it, silently, blindly, carrying its golden record through a region of space populated by trillions of icy bodies, mostly comets and comet nuclei, typically separated from one another by tens of millions of kilometers. The Oort Cloud is extraordinarily tenuous. Despite containing perhaps 1 trillion objects, the density of material is so low that the probability of Voyager 1 colliding with anything is essentially zero. It will drift through this vast reservoir of frozen leftovers from the solar system's formation, encounter nothing, and emerge on the other side. 30,000 years in the Oort Cloud. Recorded human history, from the first writing systems of ancient Sumer to tonight, is approximately 5,000 years. Voyager 1 will spend 6 of those spans drifting through a single structure within our own solar system. By the time it reaches the outer boundary, the civilizations we know, our languages, our nations, our institutions, our art, our science, will have been transformed beyond anything we could plausibly project. Human beings may not exist in recognizable form. Whatever intelligence inherits this planet or leaves it will look back at 2026 the way we look back at the very beginning of the Bronze Age. And Voyager 1 will still be moving at 17 kilometers per second, unchanged, indifferent to everything that has happened. Approximately 40,000 years from now, Voyager 1 will pass within 1.6 light-years of a star that, in May 2026, most people have never heard of. The star is called Gliese 445. Its catalogue designation is AC plus 79 38888. It sits in the constellation Camelopardalis, the giraffe, a faint, unremarkable constellation in the northern sky. The star itself is an M-type red dwarf, with roughly 1/3 of the Sun's mass and a surface temperature of around 3,500 degrees Celsius, compared to the Sun's 5,500. It is currently about 17.1 light-years from Earth, and it is generally moving toward the solar system at about 119 kilometers per second. That last fact is the key to the encounter. Voyager 1 is moving at 17 kilometers per second. Gliese 445 is moving at 119 kilometers per second toward us. The star is covering ground more than 7 times faster than the spacecraft. By the time the closest approach occurs, in roughly 40,000 years, Gliese 445 will have moved to within about 3.5 light-years of our Sun, making it temporarily closer to us than Proxima Centauri is today. And Voyager 1, drifting outward on the trajectory set by the Titan flyby in 1980, will pass within 1.6 light-years of it. It is worth pausing on a detail that is easy to miss. Voyager 1 is not heading toward any particular star. The Gliese 445 encounter is not a mission objective, a planned flyby, or a navigation target. The spacecraft was sent on the trajectory determined by the geometry of the Titan flyby and nothing else. Flung 35 degrees above the ecliptic plane by the gravitational exchange at Saturn, and aimed at no particular destination. The mathematics of stellar motion simply worked out over tens of thousands of years, so that Gliese 445's own rapid approach toward the solar system brings it into the path of a spacecraft that was never aimed at anything more distant than Saturn's moon. 2 objects, moving through the galaxy on entirely independent courses, brought within 1.6 light-years of each other by pure geometry. That distance, 1.6 light-years, is worth contextualizing carefully. Proxima Centauri, the nearest star to our Sun today, is 4.2 light-years away. The Voyager 1 Gliese 445 encounter will therefore be a closer approach to another star than the closest star in our current neighborhood. Not by a little. Voyager 1 will, briefly, be more than twice as close to Gliese 445 as we currently are to our nearest stellar neighbor. And yet, this is not a close encounter in any meaningful physical sense. 1.6 light-years is equivalent to approximately 100,000 astronomical units, 100,000 times the Earth-Sun distance. The spacecraft will not enter the star's planetary system. Its trajectory will not be meaningfully altered by the star's gravity at this range. There will be no dramatic event of any kind, just the silent passage of a piece of 1970s engineering through the outer reaches of another star's gravitational territory. For the first time in its history, another star's gravity will be stronger than the Sun's. The spacecraft that left Earth on September 5, 1977, will, briefly, be in the gravitational territory of Gliese 445 rather than the Sun, and then it will pass through, and the Sun will recede further still, and Voyager 1 will continue outward, deeper into the galaxy. In roughly 300,000 years, 300,000 years after Voyager 1 goes silent, it will have its closest stellar encounter of all. The spacecraft will encounter TYC 3135 52-1, a main sequence star at a distance of around 0.965 light-years, closer than any other star will come to it across the entire trajectory researchers have been able to map. This star is so dim and so obscure that it carries only a catalogue number. No common name, no mythology attached to it, no particular scientific fame, but it will be the nearest neighbor Voyager 1 will ever have. At 300,000 years, some perspective is useful. Modern anatomically human beings, Homo sapiens, our species, have existed for approximately 300,000 years. The entirety of that span, from the first anatomically modern humans on the African continent, through the development of language, art, fire, agriculture, writing, civilization, science, and everything that has happened in recorded history, fits within the time between now and Voyager 1's encounter with TYC 3135 52-1. Our entire existence as a species is the measuring stick for this single leg of the spacecraft's journey. 5 billion years from now, the Sun will die. This is not poetry or metaphor. It is physics. The Sun is a main sequence star, powered by the fusion of hydrogen into helium in its core. It has been doing this for approximately 4.6 billion years. Since the solar system formed from a collapsing cloud of gas and dust, it will continue for approximately another 5 billion years. And then the hydrogen in its core will run low. The core will contract under gravity, and the outer layers of the Sun will begin to expand. Slowly, at first, then enormously. Over the course of roughly a billion years, the Sun will swell into a red giant, a bloated, cool, dim star perhaps 200 times its current diameter. At its largest, it will almost certainly engulf Mercury and Venus. The fate of Earth is debated, but in most models, Earth will either be consumed by the expanding Sun, or, if it survives physical engulfment, will be reduced to a scorched, airless rock with no oceans, no atmosphere, and no life, orbiting what will by then be a dying ember of a star. Long before any of this, the Sun's gradual brightening over billions of years will have made Earth uninhabitable. The oceans will boil. The atmosphere will be stripped away. Life, if any survives that long in any form, will have needed to find other homes. The pyramids of Giza will be gone, not eroded, gone. The plate tectonics that built the continents will have rearranged the land masses so thoroughly that the very location of Egypt will be unrecognizable. The Nile will not exist. The Mediterranean may not exist. Every monument, every city, every structure of any kind that human beings have ever built will have been dissolved into the geological processes of a world that has been fundamentally remade several times over. And Voyager 1 will be somewhere around 850 astronomical units beyond where the Sun currently sits, nearly 3 times its current distance from Earth, drifting silently through the changed galaxy, carrying a golden record on which a woman's heartbeat was encoded in 1977, intact, still moving at 17 kilometers per second. The interstellar medium through which it will have been traveling for nearly 5 billion years will have done some damage. Interstellar dust grains moving at high relative velocities will have gradually abraded the surfaces of the spacecraft over geological timescales. The gold plating on the record may have thinned. Some of the more fragile external components will have degraded, but the fundamental structure, the aluminium chassis, the main bus, the heavy components, is likely to survive in recognizable form far longer than this. Scientists who have studied the long-term durability of the Voyager probes have noted that the erosion rate in the interstellar medium, while real, is extremely slow, and that the basic metal structure of the spacecraft should endure for timescales that strain our ability to express them in ordinary language. In roughly 4.5 billion years, slightly before the Sun reaches its red giant phase, the Milky Way will begin one of the most dramatic events in the history of the local group of galaxies. It will begin to merge with the Andromeda Galaxy. Andromeda, also known as M31, is the nearest large galaxy to our own. It is currently approximately 2.5537 million light-years away, and it is approaching, not slowly. At roughly 110 kilometers per second, Andromeda is on a direct collision course with the Milky Way, and in approximately 4.5 billion years, the two galaxies will begin to interact. Galactic mergers are not the explosive, violent events that the word collision might imply. Galaxies are so predominantly empty space that individual stars almost never physically collide during a merger. What happens instead is gravitational. The two galaxies pull at each other, distorting their spiral arms, scattering stars into new orbits, creating enormous tidal streams of stellar material that arc across hundreds of thousands of light years. The process is slow by human standards, but fast by cosmic ones. It will take hundreds of millions of years for the two galaxies to pass through each other and then pull back and pass through again. A complex gravitational dance that may take 1 billion years or more to settle into a stable configuration. The result, astronomers believe, will be a new merged galaxy, sometimes informally called Milky, elliptical in shape, with none of the elegant spiral structure of either Milky Way or Andromeda. Our Sun, if it still exists, will be in a completely different position relative to the galactic center than it occupies today. The night sky will look nothing like the sky you see from Earth right now. And Voyager 1 will be somewhere in the outer reaches of this new merged galaxy, its trajectory gradually shaped by the changed gravitational landscape continuing outward. Where exactly, at this resolution of time and distance, nobody can calculate, but it will be going. And then, far beyond all of this, far beyond the merger, far beyond the death of the Sun, far beyond anything in the conventional story of our solar system, the universe itself will begin its own kind of dying. The main sequence stars that fill the galaxy today, stars like our Sun, powered by hydrogen fusion, have lifespans of billions to tens of billions of years. The Sun, a reasonably average star, will last about 10 billion years total. The most massive stars burn out in millions of years. The smallest, most frugal red dwarfs, like Gliese 445, are so efficient with their hydrogen fuel that they can last for trillions of years. A red dwarf with 1/10 the mass of the Sun may burn steadily for 10 trillion years before its fuel runs low. 10 trillion years. The current age of the universe is approximately 13.8 billion years. A 1/10 solar mass red dwarf can outlive the current age of the universe by a factor of roughly 700. But even these extraordinarily long-lived stars will eventually exhaust their fuel. And as they do, one by one, over trillions of years, the galaxy will grow darker. New star formation will slow and then stop as the raw material for new stars, the gas clouds and nebulae, is gradually used up or ejected from the galaxy. The remaining stars will burn out. The galaxy will transition from a bright, star-rich spiral to something dim, populated by the cooling remnants of what stars used to be. White dwarfs, the hot, dense cores that remain after sun-like stars exhaust their fuel and shed their outer layers. Neutron stars, the collapsed remnants of stars massive enough to end in supernovae. Matter so dense that a teaspoon of it would weigh 1 billion tons. And black holes, the most extreme endpoints of stellar evolution. Objects whose gravity is so intense that not even light can escape. This era of stellar remnants, called the degenerate era by astronomers, will last for an almost unimaginable stretch of time. Trillions upon trillions of years. In this era, the occasional collision between two white dwarfs or two neutron stars might produce a brief, brilliant flash of light, a supernova without a parent star, a detonation of two dead things colliding in the dark. But between such events, there will be essentially nothing. No stars shining, no light except the faint, rapidly cooling glow of white dwarfs slowly radiating the last of their heat into a universe that grows colder and darker with every passing trillion years. James Oberg, a space journalist and science writer, collaborated with a colleague to calculate the probable fate of the Voyager spacecraft across these timescales. They concluded that somewhere in the multi-trillion-year window, both Voyager probes are likely to have drifted through the outskirts of other star systems, passing within distances comparable to the Sun to Pluto distance, at least statistically. And after the last stars have gone dark, in a universe populated by remnants and shadows, Voyager 1 will still be drifting through a completely unrecognizable cosmos, free of main sequence stars, populated almost exclusively by black holes and stellar remnants, the only source of significant illumination. The once-in-a-trillion-year collision between two stellar remnants, producing a supernova flash in the dark. The pyramids of Gliese will have been gone for 4.9999 trillion years. The Earth will have been gone for nearly 5 trillion years. The Sun, swollen, spent, cooled to a black dwarf after its white dwarf phase, will have been dark for billions of years. The Milky Way, as a structure of shining stars, will have been unrecognizable for trillions of years. And Voyager 1 will still be moving. A 1-ton machine made of aluminium and copper and gold, built in a laboratory in Pasadena, California, in the 1970s, by human beings who wanted to know what the outer solar system looked like, still moving. We have been traveling enormous distances tonight. We have moved through tens of thousands, millions, billions, trillions of years. We have watched Earth burn and stars go dark and galaxies collide. It is easy, in all of that, to lose sight of something that matters more than any of those numbers. This spacecraft was built by people, not by an institution, not by a government program, not by an abstraction called NASA or JPL or the United States of America, by specific people with specific names who showed up to work every morning in a building on the edge of a dry California valley and put this thing together, component by component, with their hands and their minds and the best engineering knowledge available to them in the mid-1970s. People who argued in meeting rooms about which instruments to include and which to leave behind because there wasn't enough power for all of them. People who debated which trajectory was worth the trade-offs it required, whether Titan was worth giving up Uranus and Neptune. People who stayed late running calculations on computers that had a fraction of the processing power of a modern smartphone, checking and rechecking the orbital mechanics that would need to be exactly right for the gravity assist to work. People who went home for dinner and came back the next morning and kept working. People, in short, exactly like the people who are going to be listening to this tonight before they fall asleep. The man who served as Voyager's project scientist for more than 4 decades was a physicist named Edward Stone. He was working at Caltech, the California Institute of Technology, when he was selected for the role in 1972, 5 years before the launch. He was 36 years old. He had never, at that point in his career, worked on a project that would define his life. Most people who go to work don't know, on any given morning, that they are walking into the project that will still be running when they are in their late 80s. Ed Stone would be involved with the Voyager mission into his mid-80s, still attending mission briefings, still reviewing data from a spacecraft that had outlasted most of the careers of the people who built it, still present in one form or another for every major milestone. The Jupiter encounter, the Saturn encounter, the crossing of the termination shock, the crossing of the heliopause. He was there for all of it. When Voyager 1 made its closest approach to Jupiter in March 1979, and the data began flowing in, the volcanoes on Io, the impossible braided ringlets of Saturn's rings, the complexity and violence of Jupiter's atmosphere in close-up. Ed Stone described the atmosphere in the control room as something like euphoria. Years later, when journalists and historians asked him what it was like to still be working on the same mission, after nearly 50 years, he described it the way a man describes something he has thought about carefully and arrived at a simple answer to. He said the mission had been a great privilege, the opportunity to go where no spacecraft had gone before, and to understand things about the universe that no one had understood before. That is the whole sentence. Not breathless, not grandiose, not the language of a man performing his own significance, just the plain, considered language of someone who had spent decades paying very close attention to something extraordinary and was sufficiently at peace with what he had seen that he did not need to dress it up. Ed Stone retired from his role as Voyager project scientist in 2019, after 47 years. He was 83 years old. The mission continued without him, as missions do, staffed now by engineers who were born after Voyager 1 launched and who inherited a spacecraft they had never had the chance to build. And then there was Carl Sagan. Carl Sagan is the most publicly familiar name attached to the Voyager mission, and for reasons that go beyond any single contribution. He had been a consultant and advisor to NASA since the 1950s. He had briefed the Apollo astronauts before their moon missions, those conversations in which he tried to explain to men about to walk on the moon what the moon actually was, geologically and scientifically, so they would know what they were looking at. He helped design and manage missions including Mariner 2 to Venus, Mariner 9, Viking 1 and Viking 2 to Mars, and the Voyager mission itself. He was a member of the Voyager imaging team. In that role, he spent years advocating for something that the Voyager program's leadership initially considered wasteful, technically risky, and scientifically unjustifiable. He wanted to turn the cameras around, point them back at the solar system, and take one final photograph of Earth. Sagan had the original idea in 1981, after Voyager 1 had completed its encounter with Saturn. He realized that because the spacecraft was so far away, the images might not show much, and this was precisely why he and others on the team felt the images were needed. They wanted humanity to see Earth's vulnerability, to illustrate what a small place it occupies in the universe. The leadership of the Voyager program was not immediately persuaded. The engineering concerns were real and specific. Pointing the cameras of a spacecraft that had limited power and limited remaining camera lifetime within a few degrees of the Sun was a genuine risk. If the optics were damaged, they could not be repaired. The cameras were a finite resource, and the scientific return, images of distant planets as tiny, unresolved dots, was, by any objective measure, minimal. There was nothing scientifically interesting about a photograph of Earth from 4 billion kilometers away that a telescope could not already tell you. What Sagan was proposing was not a scientific photograph. It was a philosophical one. The Voyager team turned down several requests to take the images, citing limited engineering resources and the potential danger of pointing the cameras toward the Sun. It took 8 years and 6 requests to get approval. 8 years, 6 requests for one photograph. By 1989, Voyager 1 was approaching the edge of the planetary system, beyond Neptune, and the cameras were going to be powered off permanently to conserve energy for the remaining mission. This was the last possible moment. It was only after Voyager 1 had completed its encounter with Neptune, after there were no more planets to photograph close up, that NASA Administrator Richard Truly finally approved Sagan's idea. On February 13, 1990, Voyager 1 warmed up its cameras for 3 hours. Then the spacecraft's science platform was pointed at Neptune, and the observations began. After Neptune, it took images of Uranus, Saturn, Mars, the Sun, and then Jupiter, Earth, and Venus. The Earth images were captured at 4:48 in the morning, Greenwich Mean Time, on February 14, 1990, Valentine's Day. Earth appeared as a tiny point of light, a crescent only 0.12 pixel in size, caught in the center of scattered light rays that resulted from the necessity of pointing the camera so close to the Sun. By coincidence, one of those rays of scattered light intersected directly with Earth, making the pale blue speck appear to float suspended in a sunbeam. That coincidence, the scattered sunbeam intersecting with the dot of Earth, was not planned. It was not engineered. It was just the geometry of where the Sun was relative to the camera and the planet on that particular morning. The universe arranged itself, without any assistance from anyone, to make the image more beautiful than it needed to be. 34 minutes after the Earth images were captured, at 5:22 GMT on February 14, 1990, Voyager 1 powered off its cameras forever. Mission planners wanted to save the energy for the long journey ahead. The data from the camera was stored on an onboard tape recorder. Transmission to Earth was delayed by the Magellan and Galileo missions being given priority use of the Deep Space Network. Between March and May 1990, Voyager 1 returned 60 frames back to Earth, with the radio signal traveling at the speed of light for nearly 5.5 hours to cover the distance. The last of the image data arrived on May 1, 1990. Sagan wrote about the image 4 years later in his book, Pale Blue Dot. He did not describe it in the language of astronomy or physics. He described it in the language of a human being who had looked at a photograph of his home from an enormous distance and felt something specific and serious about what he saw. He described Earth as a pale blue dot suspended in a sunbeam. He wrote that on it. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. That image, that 0.12 pixel fragment of reflected sunlight, is the last time Voyager 1 ever looked at the planet it came from. It has not looked back since. The cameras are off permanently. The tape recorder that stored the images is off. The spacecraft points its antenna forward into the growing dark, transmitting its data to a planet it can no longer see and will never see again. But the most quietly extraordinary human story attached to Voyager 1 is not Carl Sagan's 8-year campaign for a photograph. It is a 12-inch disc of gold-plated copper bolted to the side of the spacecraft. The golden record. In the spring and summer of 1977, with Voyager 1's launch date approaching rapidly, a small committee gathered in New York with a mandate that was simple to state and essentially impossible to execute properly. They were asked to represent Earth, to select the sounds, images, and music that could explain to any intelligence that might, in some improbably distant future, encounter this spacecraft, that something had lived here, that something had thought and felt and made things and cared deeply about other things. Carl Sagan led the project. The creative director was a writer and science communicator named Anne Druyan. The team also included astronomer Frank Drake, who created the Drake equation for estimating the number of technologically communicating civilizations in the galaxy, producer Timothy Ferris, artist John Lomberg, and ethnomusicologists Robert E. Brown and Alan Lomax. The record was conceptualized and produced in less than 2 months. A fire drill with nothing less at stake, in the words of one team member, than first contact itself. The record had to be designed, assembled, tested, physically pressed onto gold-plated copper, and mounted on the spacecraft before the launch window closed. Everything that would ride this disk into the galaxy for billions of years had to be chosen in weeks. What they chose tells you something important about what human beings reach for when they believe they are making a permanent statement. The record contains 118 photographs, 90 minutes of music, greetings in 55 human languages and 1 whale language, an audio essay on the history of Earth and life, and a poetic salutation from the Secretary-General of the United Nations. The greetings span an extraordinary range of human history. The oldest is in ancient Akkadian, the language of ancient Sumer and Babylon, spoken in Mesopotamia roughly 6,000 years ago, at the very dawn of recorded civilization. The newest Greek in the languages of 1977, and among all of them, the English greeting was spoken by a child. Nick Sagan, Carl's young son. A child's voice as the first English words humanity offered to whatever might be listening, across whatever distance, across whatever span of time. The sounds of Earth chosen for the record were not chosen for their scientific information value. They were chosen because they were true, because they were the actual sounds of the planet as it existed in 1977. Wind across an open space, rain on a surface, thunder, the breaking of ocean surf, frogs, crickets, a dog barking, birds, the low, complex songs of humpback whales, those long, liquid, haunting vocalizations that travel for miles through deep ocean water, communicating something specific between animals whose communication we still don't fully understand. And underneath all of it, running through the record like a heartbeat, because it literally is one, the sound of human life at its most basic. Footsteps on gravel, laughter, a baby crying, a mother's first words to her newborn child, and the sound of a kiss. Someone sat in a room in 1977 and decided that among the sounds that best represented Earth and human existence, a kiss deserved to be there. On a spacecraft that will still be moving through the darkness of an almost unrecognizably changed universe long after the last stars have gone out. A kiss. The music selection was, as Andrewen later described it, its own kind of fire drill. The selection included music by Bach, Beethoven, Mozart and Stravinsky, alongside Louis Armstrong, Chuck Berry, Blind Willie Johnson, and musicians from cultures across the world: Indonesia, India, Peru, Bulgaria, Senegal, and more. The Chinese piece Flowing Streams, 2,500 years old, was included after Druyan tracked it down through months of searching. Sagan's team wanted to include the Beatles song Here Comes the Sun, but the record company EMI, which held the copyright, declined. The Beatles themselves supported the idea. EMI said no. Andrewen later said this was one of those cases of having to see the tragedy of our planet, a chance to send a piece of music into immortality, declined for reasons of money. But the most remarkable thing on the Golden Record is something that most people, even people who know about the record, have never heard about. Andrewen, the creative director, had an idea. She wanted to record the electrical activity of a human brain, an electroencephalogram, an EEG, and encode it as audio on the record. Her reasoning was, would it be possible, I wondered, for a highly advanced technology of several million years from now to actually decipher human thoughts? Sagan and the team loved the idea. Druyan volunteered to provide the brainwaves. The recording was scheduled for June 3, 1977. 2 days before the recording, on June 1, 1977, something happened that Druyan had not anticipated when she scheduled it. Druyan had been searching for months for a piece of Chinese music to include on the record. She had finally found it, Flowing Streams, a 2,500-year-old composition. In her excitement, she called Sagan, who was traveling, and left a message at his hotel. An hour later, Sagan called back. By the end of that phone call, Druyan and Sagan were engaged to be married. They had been friends and professional collaborators for 3 years. They had been in each other's company countless times during the making of the record. And in one phone call, initiated by the discovery of an ancient Chinese melody, the relationship changed completely. Druyan describes it as a eureka moment, like a scientific discovery. She screamed out loud when she hung up the phone. 2 days later, she went to Bellevue Hospital in New York City, lay down, and meditated for an hour while the sounds of her brain and body were recorded. During the recording of her brain waves, Druyan thought of many topics, including Earth's history, civilizations and the problems they face, and what it was like to fall in love. The hour of recording was electronically compressed into a single minute of audio, a minute that sounds, according to Druyan herself, like a string of exploding firecrackers. That minute is on the Golden Record, on Voyager 1, in interstellar space, moving at 17 kilometers per second through the dark between the stars. The brainwaves of a 27-year-old woman, 2 days after she fell in love, thinking about love and history and the wonder of being alive, encoded in gold and bolted to a spacecraft that will outlast the sun. Druyan and Sagan announced their engagement 2 days after Voyager 2 launched, on August 22nd, 1977. They married in 1981 and were together until Sagan's death in December 1996. The love that began in that phone call over the discovery of a 2,500-year-old Chinese melody. That love is on the record too, not symbolically, literally, encoded in the grooves of the gold. Sagan, reflecting on what it meant to send the record outward into the cosmos, wrote that the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. He was right. And the specific contents of that bottle confirm it. When given the opportunity to say something permanent, something that might outlast the Earth itself, the people who built Voyager 1 chose to include a heartbeat, the sound of a kiss, whale song, the laughter of a child, a 2,500-year-old melody, and the brainwaves of a woman thinking about love. Not a list of achievements, not a record of political systems or military capabilities or economic output, not an attempt to impress or intimidate, just the sounds of a planet that was, in 1977, very much alive. Those sounds are out there tonight, moving at 17 kilometers per second through the interstellar medium, carried on a disk of gold-plated copper that was designed to last without significant degradation for at least 1 billion years. Going as Voyager 1 has always been going, away from us, but carrying us with it. Everything we have discussed tonight, the Grand Tour alignment, Gary Flandreau's calculation in 1965, the volcanoes on Io confirmed 3 days after Peale and Casson and Reynolds predicted them, the braided ringlets of Saturn, the thick orange haze of Titan, the 35-year journey to the heliopause, the plasma oscillations that Don Gurnett's team detected on April 9th, 2013, and that caused a room full of physicists to jump out of their seats. We have walked the deep time trajectory, 300 years to the Oort Cloud, 30,000 years to cross it, 40,000 years to pass within 1.6 light years of Gliese 445, 300,000 years to brush within less than a light year of TYC 3135-52-1, 5 billion years to watch the sun swell and die, 4.5 billion years to watch the Milky Way and Andromeda begin their slow gravitational merger, 10 trillion years to watch the last red dwarf exhaust its fuel and go dark. We have met the people. Ed Stone at his desk for 47 years paying attention. Carl Sagan arguing for 8 years and through 6 rejections for one photograph that would show humanity what it looked like from far enough away to see it whole. Anne Druyan lying in a hospital bed in Bellevue, thinking about love, while machines recorded the electrical patterns of her brain and transferred them to a gold-plated disc that is now moving through the interstellar medium at 17 kilometers per second. And we have sat with the present tense, the Big Bang being planned at JPL right now, the 2 remaining instruments still transmitting, the stepper motor on the LECP still running at half a watt, in case there is a chance, however slim, to bring the instrument back. All of that is done now. All of that has been given. What remains is this, a point of light moving through the dark, 17 kilometers per second, no destination, no one waiting, no instruction to follow, just the physics of a frictionless medium and a moving object playing out in the only way they can, going. And here, in the quietest part of this long night, I want to try to say something about what I think the Voyager 1 story actually is. Not the scientific story. We have told that carefully. Not the human story. We have told that too. But the thing underneath both of them, the thing that remains when the facts have been given and the names have been named and the timescales have been walked. I think the Voyager 1 story is a story about permanence. not our permanence. We are not permanent. The evidence of human history is not that human beings persist. It is that human beings try, and sometimes what they make outlasts the trying. Most of what we build will be gone within a few centuries, almost all of it within a few million years. The planet itself within 5 billion. The idea that anything we make could survive the universe is, by every ordinary measure, absurd. And yet, a disk of gold-plated copper pressed with the sound of a heartbeat and a kiss and the brainwaves of a woman newly in love is moving right now through the space between the stars. It will still be moving, intact or nearly intact, when the last star in the Milky Way burns out. It will still be moving when the last star in the galaxy formed by the merger of the Milky Way and Andromeda burns out. It will still be moving in a universe that is almost entirely dark, populated by the cold remnants of things that used to shine. Not because we are permanent, because the void is. The void between the stars is the most stable environment in the known universe. No friction, no oxygen, no water. No gravity strong enough at these distances to pull anything down or grind anything away. In the void, a moving object continues to move. A structure that does not rust continues not to rust. A disk, pressed with the sounds of a living planet, continues to carry those sounds, inert and unchanged, through the dark. We sent Voyager 1 into the one place where our things do not decay. And in doing so, without quite intending it, without any mission objective that said, make something that outlasts the stars, we accidentally made the most permanent thing our species has ever produced. There is a question that has been hovering at the edges of this night, and I want to name it now, in this quiet stretch of time, before we drift towards sleep. If Voyager 1 is still out there, drifting through a universe that has gone dark, past the death of the Earth and the death of the Sun and the death of the last stars, is there anyone to find it? It is the question the Golden Record was designed around. Carl Sagan and Ann Druyan and Frank Drake and the rest of the committee spent weeks choosing what to put on the record precisely because they were taking seriously, not as a certainty, but as a genuine possibility, that something out there might one day pick it up, not soon, not in any time frame that connects to us, but in the long, open future of the universe, in some improbably distant encounter between the drifting spacecraft and some other intelligence in some other corner of some galaxy that may not yet exist. Something might find it. Sagan was careful about this. He did not pretend the probability was high. He said the chances were small, and some people said infinitesimal, and he agreed that this was probably right, but he said the record was worth making anyway, and I think he was right about that too. Not because of the odds, because of what the act of making it says about us. When a species that knows it is temporary, a species that knows its planet will eventually be consumed, and its sun will eventually die, and its civilization will eventually be replaced or ended by forces it cannot fully predict. When that species decides to make something and send it outward with the sounds of its own life, that is a statement about what it values, not what it owns, not what it controls, what it loves. Whale song, a child saying hello, the brainwaves of someone in love. These are the things they chose, and those things are out there now, moving at 17 kilometers per second through a silence that has never been broken by any human sound before, carrying, against all probability, the evidence that once, on a small blue planet orbiting an unremarkable star in the outer arm of a spiral galaxy, something lived and felt and thought and wondered about the dark. You are part of that story. Not abstractly, not metaphorically, literally. You are on the pale blue dot. You are in the frame of the photograph that Voyager 1 took on February 14th, 1990 at 4:48 in the morning. Not individually, you cannot be resolved at 0.12 pixels, but collectively, cosmically. Every human being alive at that moment was in that photograph. Every human being alive tonight is the continuation of the species that built this machine and sent it out, and has been listening for its signal, patiently, across nearly 5 decades of deep space. Voyager 1 does not know you are here. It has no capacity for knowing. It has no awareness of any kind. It is not carrying the story of your life, or your name, or your particular night. But you know it is out there, right now, tonight, as you lie here in the dark, 172 astronomical units from Earth. A machine no larger than a small car is moving through the space between the stars at 17 kilometers per second, carrying a disc of gold pressed with the sounds of the only world you have ever known. That is a real thing, not a metaphor, not a poetic flourish. A real, physical, verifiable fact about the universe you inhabit tonight. Let the narration thin out now. There are things that want to be said in long silences rather than in sentences. The sound of wind across a plain, the low song of a whale moving through deep water, the way a heartbeat sounds when it has been compressed to a minute and encoded in gold and sent across 172 astronomical units, and will still be moving in a universe where there are no stars. These things do not need explaining. They just need to be allowed to be what they are. Voyager 1 is in interstellar space tonight. The interstellar medium hums. Stellar Ocker confirmed it. A steady, narrow-band emission that persists from 2017 onward in the data. The first evidence that the space between the stars has a background voice of its own. Not a voice that communicates anything. Not a signal with content, just a hum. The universe, making a sound because that is what plasma in a magnetic field does. Because the physics do not require silence, and silence is not the default state of things. The universe hums. Voyager 1 is drifting through the hum. And somewhere on its hull, on a disk of gold-plated copper designed to survive for 1 billion years, there is a recording of a heartbeat that has been in space for almost 50 years and will be in space for trillions more. A heartbeat. In the hum. Going. We measure time in years and decades and centuries, and we call the things we build monuments if they last 1,000 years. We call them ancient if they date from 2,000 or 3,000 years ago. We speak of the pyramids as if they are unimaginably old. They are 4,500 years old. That is nothing. That is the blink before the blink before the blink, at the scale of what we have been talking about tonight. Voyager 1 will be moving in 4,500 years. It will be moving in 4.5 million years. It will be moving in 4.5 billion years. The pyramid is already dust by then. The Earth is already gone. And Voyager 1 is somewhere in the Change Galaxy, carrying the sounds of a world that no longer exists, still moving at 17 kilometers per second, still obeying Newton's first law in the frictionless dark. An object in motion remains in motion. In the deep void between the stars, there is almost nothing to act upon it. Almost nothing. Almost. For essentially practical purposes, nothing. The golden record was designed to last for 1 billion years without significant degradation. 1 billion years. The age of the universe is 13.8 billion years. 1 billion years is not a small number relative to the age of the universe. It is roughly 7% of all the time that has existed since the Big Bang. And the record is designed to last that long. Not Voyager 1's electronics, Those will fail long before then. The computers, the transmitter, the attitude control systems, all of them will be dead within a decade from tonight. But the disk itself, the gold, the grooves pressed into it, the sounds encoded in those grooves, those can last 1 billion years in the cold and frictionless dark of interstellar space without being meaningfully altered. The sound of Anne Druin's heartbeat 2 days after she fell in love. 1 billion years in gold, moving through the dark. I want to say one more thing before this night ends. It is about what the Voyager 1 story asks of us, if it asks anything at all. I do not think it asks us to feel hopeful in any forced way. I do not think it asks us to be reassured that humanity is good, or that the universe is friendly, or that things work out. The universe is not particularly friendly, and things do not always work out, and the death of the Earth and the Sun and the last stars is not a comforting prospect by any ordinary measure. But I think the story of Voyager 1 does ask us to notice something. In 1977, a group of people, engineers, scientists, mathematicians, musicians, writers, worked under significant time pressure to build something and send it out. They did not know if it would work. They did not know if anyone would ever find the record, or hear the whale song, or detect the signal from the brainwaves of someone thinking about love. They knew the odds were extremely long. They did it anyway, not for recognition. The recognition, if it ever comes, will come in a time frame so vast that no one alive today will be there for it. They did it because building it and sending it was, in itself, a statement that they thought was worth making. A statement that goes like this: we were here. We were alive. We listened to whales sing in deep water and we thought it was beautiful. We fell in love and we thought it was worth recording. We looked up at the night sky and we wondered what was out there, and we sent something to find out. We did not have forever. We had the years we had. We used some of them to press a heartbeat into gold and send it to the stars. Drift now. You do not need to stay with this. The ideas have been given. The facts have been set down. The people have been named. The timescales have been walked all the way to the end of the stars. All that is left is the dark, and Voyager 1 moving through it, and you here, wherever you are, in whatever room or bed or quiet corner you have settled into for this night. The spacecraft does not need your attention to keep moving. It has been doing that for nearly 50 years without any help. It will do it for trillions more. You can let it go now. Close your eyes if you have not already. The hum of the interstellar medium is out there, in the data, in the frequencies that the plasma wave subsystem is still picking up and transmitting back across 25 billion kilometers. Something that barely exists is making a sound, in the void, in the dark, where the only other thing moving is a disk of gold, pressed with a heartbeat, going. Tonight we asked a question that sounded simple. Why will a piece of human metal outlast every star in the Milky Way? And the answer turned out to be larger than the question. It turned out to be a story about a 175-year planetary alignment spotted by a young mathematician in 1965. About volcanoes on Io confirmed 3 days after 3 scientists predicted them. About a physicist who paid attention to the same mission for 47 years. About a woman whose brainwaves, recorded 2 days after she fell in love, are pressed into gold and moving through interstellar space right now, tonight, as you lie here. It turned out to be a story about the void, the most permanent environment in the known universe, the place where moving things keep moving, where nothing corrodes and nothing stops, and a 1-ton machine assembled in California in the 1970s keeps going at 17 kilometers per second long after the last star has gone dark. Voyager 1 will still be out there when you wake up tomorrow morning. It will be 1.5 million kilometers further from Earth than it was when you pressed play tonight. Moving, as it has always been moving, into the permanent dark between the stars, carrying a heartbeat, carrying a kiss, carrying the sound of a child saying hello to anyone who might ever be there to hear it. If nights like this one are the kind of night you come back to, if slow science, told softly, is what you want when the day is done and the world is quiet, then subscribing to Cosmic Drift is just the quiet way of making sure we're here when you need us. Sleep well.